So this is 18,000 meters down. And then the X max, X min, this is the width of the study. No, just the width of the calculation. The locking would be this 18. But this is for a dip slip case. So this is the, remember this more complicated looking equation in here. This is using this math right here. The Z is just the depth to the tip. So in this case, it would, the Z is just how far down it is to here, and X is where this point is. So XZ is the coordinate of the tip of the fault. And then this lambda is just the length of the fault. So in this case, in MATLAB, it's 18,000 right here. It's 18,000. So that's the length down. Then X max is 15,000. That would be how far we go to calculate this direction. And then minus whatever 20,000 is how far this way to calculate. And then you can see in the MATLAB, this 1,000 is just every kilometer I calculate. Okay? So then all the math is down here, and it's just doing this addition. Sort of it takes the upper dislocation, and it takes the lower one, and it just adds them. But the lower one, you see, I'll just show you one. So there's upper and lower, and you see right here, I put in the negative components of slip. So when we add it together, these negatives counteract those lower parts of the fault along the dislocation. So anyway, you don't have to worry about that part. If you just push this arrow, it should work. So you can experiment. So what this shows is actually, let's just try here. So this shows the fault, same on both sides. And then this is the X displacement. So this is, in this case, you see negative is going to the left and positive goes to the right. So it makes sense because it's a normal fault. So the left side goes down, right side goes up, right? Or it goes like this. And this is the effect of the upper dislocation. That's the effect of the lower dislocation. So it's this plus that equals this. And then here's the verticals. So upper dislocation, lower dislocation. This is that signal that looks like the Bora Peak case that I was showing. So these are we say the components, but if you use the arrows, this shows you the, both components together. So there's the fault would be right here, and it's going down like this. And so just compare this displacement with the Bora Peak case. So that's just right there. That is the same as this. Okay? So now let's change something simple. So what you would do is, let's say, well, one if it was going to be shallower. So I made it 10 kilometers deep. So then you just push this. So you can see the change. It got a little tighter. Okay? So now let's try, because I know you guys we have our, so let's do 20. Let's keep it deeper. Okay? So now what let's do is, so here's a trick, is it's dipping like, it goes 135. So if you think of dip, it starts here at 0, 90. So it's over here. The dip is 135, right? So let's try what happens if we do dip is 45. So it should change the dip, but it might change it into a reverse fault. Okay, so it's going around. So let's just look. We can tell by inspection. Yeah. So there's a 45-degree reverse fault, and you can see the, you kind of have to go between the two, what they're doing. So let's slowly build the subduction zone case. So let's make it shallow. So what do you guys like, 25 degrees for a subduction interface? So here's reverse fault, so you really see that displacement near the fault. But now let's try to make it a little bit blind. So here remember these are in, this is the upper tip in meters. So the tip is at 0. So let's just look at this again on here. So you see the top of the fault is there at 0. It goes to there. But let's say we know for a subduction zone that usually this lock part's not coming all the way to the surface, although it did in Japan, but a lot of times it's blind. So we can put the tip of the fault down 1,000 meters. Yeah, so here you can see, it's a little bit hard to see because of the scale, but you see it's down. So it makes it a little bit smoother. So if we go back, let's go make this 1 again. So don't put 0, as I said. If you make it 0, it divides by 0, so it's bad. But 1 meter below the surface is the same as at the surface. So it's very sharp. So the power of the MATLAB is you can, if you do this right, kind of get these guys to sit in here like this, and then you can rearrange your windows. Whoops. I lost it. So if I put this guy down here, so you do your windows so they're all arranged like this, there, and then get this thing a little bit lower here. So now we can kind of have our little calculation engine. So I have 1, so let's change this to 1,000. So it went a little bit deeper, starting, basically it's still, it's kind of hard to see the effect there. What it did was it pulled the tip. Yeah, so it basically rounded the edge off here. So let's try it if we go to 10,000. So if we make it really deep. So there, all you see is the uplift. So see, that's the blind. That would be if you have a deep thrust earthquake. You just lift a very smooth way. So let's try like 5,000. So maybe 2,000. Yeah. So somewhere around between 2 and 5,000, we start to get this pretty good sensitivity to the tip position.